All right, thank you. So I'm going to be talking about decoherence for fluctuations out of equilibrium. And you might note that there will be certain similarities and overlap to Andy's talk on Monday, but hopefully I can present some of the background for this in a slightly different way that maybe will be appropriate for this audience with a slightly different background. So I want to actually talk through a particular example of tuning, namely the flatness problem, which inflation solves. And then I want to, in the spirit of the topics of this conference, talk about arrow of time and Boltzmann-Brain problem, as well as decoherence. These are things that motivated me to explore a Toy-bit qubit model, where I can see in this full unitary model behavior that resembles equilibration as well as fluctuations, and then talk about the evolution of entropy and decoherence in that model. So first, to give a little background to try to set up the flatness problem, I'm going to be talking about FRW universe. This is a universe which is describing a homogeneous and isotropic universe that's either expanding or contracting. In the case I'll be talking about, it'll be expanding. So this first equation here, as we understand from gravity, and in particular Einstein gravity, there's a relationship between the evolution of space-time as well as the various energy densities or mass densities that are contained within it. Just a note, I'll be always working with units where speed of light is 1, so I'll treat energy densities and mass densities sort of interchangeably. So you can understand this equation. This first term has to do is the Hubble rate squared, which has to do with how the scale factor will evolve, and the scale factor is just giving you a sense of how much your universe has expanded or contracted. So if your universe has doubled in size, the spacing between everything has doubled, then your scale factor would have doubled. And then on the right side, you have all the different stuff in your universe, things like matter. This would be like mass density or energy density for non-relativistic matter. Then you have radiation, also including relativistic matter, and other things you could put in here if you'd like.
G is in simplified units now, right? It's not dimensionless there.
Yeah. So normally I would leave out G. I would turn it into some dimensionless thing. I am explicitly working in units where speed of light is 1 and Planck's constant is equal to 1. And often I would take G or some G times factors of pi to be equal to 1 as well. So yes, and most of my, especially my toy model, we've been working mostly in some dimensionless units. Okay, and furthermore, you can also understand how the energy densities will evolve with time, or instead of really keeping track of time, specifically with scale factor. So as the universe expands, the various things in it will dilute. And they'll dilute at different rates depending on the type of stuff it is. Specifically, the relationship between the energy density and the pressure will tell you when you solve these equations how it will evolve with scale factor. And that'll be quite important for the upcoming argument where we talk about curvature. So hopefully that's just a quick and dirty introduction to try to set up what curvature is. So on the previous slide, when I was talking about the various densities, there's going to be a critical density where if all the stuff that I put in those parentheses, the different components that make up the things in your universe, if those add up to the critical density, then your universe would be flat, spatially flat. Remember, as we understand Einstein gravity, gravity is directly tied to the curvature of space-time. So there will be some special value you set up where you will actually have a flat universe. And in an expanding universe, which is flat, you would have constant expansion. It wouldn't be accelerating or decelerating. So that seems like it would be a particularly special value, which I'll sort of try to explain why this value would be so special. And just a comment, the universe that we observe today appears to be very flat. We appear to have this density very close to the critical density. I'll explain that further. One way to sort of understand how this works, or how to parameterize what's going on, you can define sort of an effective energy density or mass density associated with the curvature, where K is the curvature. And that just has to do with how much your energy density, the sum of all your energy densities, deviates from the critical density. And if I had formulated the equations on the previous slide a little bit differently, it's often formulated in terms of this constant K, which has to do with that. Remember, I said that we're working in an FRW universe, which is homogeneous and isotropic. So this would be some constant curvature term that applies to your entire spatial slice. But if you want to consider how this quantity evolves, you have to consider how rho sub k would actually scale with scale factor. And sort of based on, if you put together the parts that I said, you would see that this rho sub k, this effective energy density, would scale as 1 over the scale factor squared, which will become relevant as I explain the flatness problem. So the different types of universes you can have just flat, you can have positive curvature, and you can have negative curvature. In particular, if we had significant positive curvature early enough in the universe, you would expect the expansion to slow down and decelerate and actually turn around and start contracting. And that'd be a case where you could have a big crunch. So it's actually quite an important observation that we are very close to flat. So and a brief thank you to Andy for letting me steal this slide. Or at least still this graph. But I think this tells a very nice picture of why there's a flatness problem if we look at the various comparisons of energy density today. Now just a comment, I haven't really said anything about this last term. This has to do with dark energy. When this story was first being told, it wasn't really realized or known that dark energy was present in the universe, but the dark energy has only become dominant very recently. So it doesn't really change the story very much in the early universe, and the same story sort of holds true. So if I presume that there's a Big Bang without inflation, and I ask what would the different energy densities have to have been early on to give me the ratio of energy densities today, based on the fact that the effective energy density associated with spatial curvature scales as 1 over a squared. And note this is a log-log plot, so the different slopes have to do with the different powers of scaling. It's going to die off much slower compared to things like non-relativistic matter and radiation. So if today our observations are consistent with no curvature, but at least there is evidence that it's less than 1%. If you were to have less than 1% today, then the ratio in the early universe, during early parts of the Big Bang, would have had to have been many, many orders of magnitude smaller, many, many orders of magnitude closer to 0. And you can see this as, I think, without even saying anything about entropy, I think hopefully a lot of you agree this seems like a very special tuning. We need to set up the universe in a very special initial state in order to get it to the state it is today, in order to ensure that nowhere in the history up to this point have you reached the point where the spatial curvature sort of takes over and you lose out on the expansion and start contracting and crunching. So this seems like quite an issue, and it's an issue that I'd say inflation solves quite nicely. We might hear more about that tomorrow during the inflation tutorial. But the basic idea of how inflation helps us out is that much like the constant energy density of dark energy today, you instead have an early period of cosmological constant like domination. And that gives you accelerated expansion of the universe, and this will kill off the spatial curvature early on, allowing you to predict these, this very low percentage at the end of inflation. So this is, I just wanted to take a brief aside to give a little background on the flatness problem, because I think this is a great example of where tunings or apparent fine tunings in cosmology have led to, has led to a call to put more into theory. If people never worried about this, then Guth might have never thought of considering inflation at all. And there are a lot of great predictions that come out of solving problems like this. There's another tuning problem it also solves called the horizon problem, as well as others. But this is just to give a little shout out to why we talk about tuning so much and what you can get out of it. So now to talk about things more generally. Yes?
So this is tuning by a large constant amount, but not infinite tuning, like requiring some parameter to be exactly some value.
Right, so you're saying compared to making the curvature just exactly 0.
Well, that's 0 is a special value, so maybe it's not a free variable. So but if it's exactly a certain amount, and the universe wouldn't work if it were more or less by any at all, then you'd have the worst problem, right? But you're talking about a large but finite amount of
It's just tuning to 55 decimal places.
Yeah. that's you know, I ate more than decimal places than that for breakfast this morning.
I mean, this is just one tuning. I didn't even bring up the horizon problem, which is another very large exponential tuning. So it is very large but finite, but usually as far as that I'm concerned, that's just as good as infinite tuning, because I don't usually, anyway, worry about infinity. But maybe now I'm going to frame things in a more general sense and just talk about, so even though inflation solves the flatness problem and other tuning problems, it doesn't sort of get you out of an inherent issue with trying to talk about a natural initial state to the universe. And this is sort of similar to what Andy said on Monday, but maybe I'll sort of frame it slightly differently. So let's say we had some understanding of where we were today, or a description of our world today. So I'm saying this is the state of either just me or the Earth, or whatever I want to say is I'm confident in describing my state as. Maybe the minimal thing that I'm happy describing is just my experiences in my brain, but maybe you'd rather talk about our best account for entropy in the universe, whatever you want to put there. This is our state today. And if we wait around a tiny bit, things seem to evolve as we expect, which is entropy will most likely increase because we are not in a maximum state of entropy. So we wait around a little bit, and pretty much for every macroscopic process that we can observe, the entropy of everything, our best account for everything, seems to be increasing. So that seems very nice. That agrees with statistical mechanics and thermodynamics and most everything we understand. And now, as cosmologists want to do, we want to talk about how did we get here. So the best story that we have that seems consistent with what we observe describes a much lower entropy initial state, be that the Big Bang that I was talking about before, or you can have an even lower state with inflation. Yeah, question?
This question already a couple of days ago. What is the definition of entropy?
Good. So here I'll typically, so that can sometimes be a tricky question. In the model I'll be talking about, I'll explicitly work with von Neumann entropy. But usually, oftentimes in this picture will mean sort of typical thermodynamic entropies. Usually you're sort of coarse graining in sort of a usual way to define entropy in a usual sense. When we're talking about like today, for example, usually they can count for things, you're usually describing sort of normal stuff in sort of a state of at least like small local systems near equilibrium, or you can, I don't know, that's sort of my rough answer. I'd say it's not always super precise, but you get the right idea, sort of not that sensitive up to your precise definition or precisely how you're counting.
So this is like adding up all the entropy of the cosmic background radiation and the stars considering it to be masses of hot gas,
Ye-
not perversely correlated with each other so as to have zero entropy.
Right, yes. And I'll comment on that a little bit. If you thought of the whole universe as a pure state, then the von Neumann entropy of the whole universe would be zero if you included enough. But I'll sort of comment on that a little bit.
Henry, to draw a plot like that, you're actually mostly talking about black holes.
Yeah, that's fair. That's true. For me to really do this sort of extrapolation, I am mostly talking about black hole entropy. So I'm using really a generalized second law where you include, it's pretty well accepted that the black hole entropy scales with its area. There are a lot of thought experiments that sort of, if you want to keep the second law.
The entropy in the universe now is black holes, right?
Yes, right now. Yes, that's true.
So we're using then the normal entropy of a black hole. And
Well,
just trying to understand if we're talking about classical entropy or quantum.
so
Because, I mean, yeah.
yeah, so that's a good question. So I would say that, there isn't really a perfect understanding of how to, what the entropy of a black hole is counting exactly. We don't have like a good microstate counting example. And there are various thought experiments where you think about things like, leading to the black